Hello and good day, pre-algebra. We are tackling unit number 9. We skipped ahead to CO66, and this unit is going to cover some things on probability, which you've probably had before. But just kind of hit the highlights. Today we're going to talk about something called the counting principle and then how to calculate probability. We'll get into experimental and theoretical probability. And just see where the rest of the year takes us. So let's start by defining what is probability. I know you've heard the word before. You've not only studied it before, but you've had experience with it before. What is probability? How would you define it? Aiden.
Like the chance that you're going to get, like the chance that something's going to happen.
Okay, the chance that something's going to happen. Anyone else want to expand on that? All right, I'm gonna change your word chance to likelihood. Okay, probability is the likelihood of an event happening. Okay, the likelihood of an event happening. Okay. And this is fitting that we just finished a unit on percentages, because oftentimes you'll hear probability in terms of percentage, right? There's a 75% chance of rain tomorrow. What does that really mean, right? What does it mean for there to be a 75% chance of rain tomorrow? John?
There's out of 100 of 75. Out of 100 there's 75. So 70, you said 75, right?
Yeah.
So it's more likely.
It's likely to happen, right? Basically, 75% chance of being rain tomorrow means that if the weather conditions tomorrow happened 100 times, 75 of those times, it would result in rain, right? So the likelihood of an event happening. So the scale of probability runs from 0% to 100%. This is a situation where it is not possible for there to be a percentage greater than 100%, right? If something is guaranteed to happen, it has a 100% chance. There cannot be a 110% chance of an event occurring. Okay, so 0 to 100%, 50%. I'll put that up here. 50% would mean that there's just as much chance of it happening as not happening. Flipping a fair coin, 50% chance landing on heads, 50% chance landing on tails. Okay, 25% is kind of another marked point here, and anything kind of in this range is considered not likely to happen. Okay, not likely to happen. 25% chance will be 1 out of 4. Okay, anything kind of in this area. So 20% chance, 33% chance, 40% chance, all those would be not likely to happen. Above 50%, we mentioned 75%. This range of things would be likely to happen. Okay, 60%, 75%, 80%, 90%, all those things would be likely to happen. Okay? And what we're going to focus on today is not calculating the probability of an event happening, but how to tell how many things could happen. What are the possibilities? Because probability, the formula of it, is essentially what you want to happen over what could happen. Today we're going to focus on the what could happen piece. How many outcomes exist? So this first example here, and I'm going to scroll down so we can get both examples on the page. Anyone still need these notes? Are we good? Okay. All right. Also, we're done with the flipped classroom. That was fun. I had a great time, but I think we're going to go back to the normal way to do it. Is that cool with everybody?
Yep.
Okay. All right. Okay. So we have the situation here. We're flipping a coin 3 times. How many possible outcomes are there? Leah, do you have a question? You may. Aiden, you have a question? Oh, well, let's. What do you think?
I think there's 3 possible options.
3. We will test if that is correct. Okay. And one way to kind of visualize this is by using a probability tree. If we're flipping a coin 3 times, I want you to do this as best as you can spatially, because you don't want to scrunch it all in just one area here. But we're going to start kind of here in the middle. All right. And what could happen on flip number 1? What could happen on flip number 1? What are the possible outcomes for flip number 1? Annika. We could get a heads, or we could get a tails. Okay? On flip number 2, let's say we got a heads the first flip. What could happen on flip number 2? Sasha. Heads or a tails. So from this heads, I'm going to draw out 2 more lines, one with heads and one with tails. Okay? If we flip the tails the first time, what could happen the second time? Aiden. Heads or tails again, right? So I'm going to draw out another 2 lines here. Here's where I always get lost, this bottom one. It looks so good until I get to that part there. Then okay? But already we're at 4 options here, right? One option, if we only flip a coin twice, the 4 outcomes that we get, either heads, 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 tails, tails, heads, or tails, tails, right? Each branch of this tree represents one possible outcome. So our prediction of 3 has been proven wrong here, because already we're at 4. Let's see what happens on flip number 3. Okay? If we get a heads the first time and a heads the second time, what could we get the third time? Annika. Heads or tails again, right? It really doesn't matter what comes before. Every time we flip this coin, we could get a heads or a tails. Okay? If we flip a head the first time, a tail the second time, what could we get on the third flip? Everybody. Heads or tails? If we get a tails the first time, a heads the second time, the third flip, we could once again get either a heads or a tails. And if we flip a tails the first time, a tails the second time, once again, that third flip, we're either getting a heads or a tails. Whew, just barely fit it in there. Okay. And now what this gives us is it gives us a visual representation of our outcomes. Right? Every branch of this tree from beginning to end is a possible outcome. If we go from heads to heads to heads, that's the outcome of getting 3 heads in a row. Right? If we go from heads to heads and then the third flip we get a tails, well, that's another outcome. Heads, heads, tails. Aiden.
What if the coin landed on its side?
I've never actually seen that in practice. And actually, the only coin that really would have a chance based on the edge would be a nickel, because dimes and quarters both have reeded edges. There's no really flat surface for it to land on. A nickel's got that flat surface. That would be the only coin where I think it would be possible, but I've never seen it done, except for in a movie. But yeah, okay. Let's say that we get a heads and then a tails and then a heads. That's the outcome of heads, tails, heads. Right? We can just follow each branch here to get all outcomes that exist. Next one is heads, tails, tails. The next one is tails, heads, heads. Then tails, heads, tails. Tails, tails, heads. And finally, tails, tails, tails. Okay? So, how many outcomes are there? Annika? There are 8, right? Each of these represents an outcome. 8 outcomes for flipping 3 coins. Yes, sir?
Can't you just count all the ones on the end?
That's what we did. Yes. Yeah. If essentially, we got 1, 2, 3, 4, 5, 6, 7, 8, right? But then actually writing out the outcomes, we not only know how many there are, but what they are, right? So that's the purpose of that 4th column there. Before we get to the counting principle, let's go down to the bottom one. You have 3 pairs of pants and 4 shirts. How many possible outfits can you make? How many different combinations of outfits can you make? So let's get some pant colors here. What color pants do we have in our closet? Give me a color. Alina. Pink. Everybody's got to have a pink pair of pants. I actually do have a pink pair of pants. Give me another color. Something that doesn't start with P, just so we can kind of keep it relatively simple. Gavin. Blue. Of course. Okay, give me a third color. Doesn't start with a P or a B. Yellow. Okay, so we'll represent pink with P, blue with B, and yellow with Y. How about our shirts? 4 shirt colors. If you can help it, not P, B, or Y. We're really going to challenge ourselves here. Make it B. Green. Okay. Leah? Orange. Sarah? Red. I'm impressed with your knowledge of colors. Maggie C. Turquoise. Oh boy. I'm lucky I know how to spell that. Turquoise. Okay, so pink, blue, yellow, PBY for pants and shirts, green, orange, red, or turquoise, GORT. So the question is here, we have 3 pairs of pants and 4 shirts. How many possible outfits can you make? Okay, so you are choosing your outfits here, right? Here's you starting here. What options do you have for pants? You've got pink, blue, yellow, right? So our first option here, we'll put pants up at the top because that's what we're choosing here. We need 3 branches coming out of this starting point. 1 for pink pants, 1 for blue pants, and 1 for yellow pants. Right? You pick your pair of pants, those are your 3 options. Pink, blue, yellow. Then you go ahead and you pick your shirt. If we pick a pink pair of pants, never mind whether or not we match, because who really cares about that? But if we pick a pink pair of pants, how many options do you have for shirts? Yeah. 4 of them, right? You could wear a pink pair of pants and a green shirt, look like a watermelon. You could wear a pink pair of pants and pick an orange shirt. You could wear a pink pair of pants and wear a red shirt, or you could wear a pink pair of pants and wear a turquoise shirt. Those are your 4 options. Pink pants, green shirt, pink pants, orange shirt, pink pants, red shirt, pink pants, turquoise shirt. If you pick your blue pants, what shirt options do you have? Maggie? The same 4, right? You could go with your green, you could go with your orange, you could go with your red, you could go with your turquoise. And if you pick out your yellow pants, what shirt options do you have? Sasha? The same 4. You could do green, orange, red, or turquoise. That probably tree does not look very tree-ish at all. Sorry about that. Okay? But at the end of the day, its purpose is to tell us how many outfit combinations you have. How many outfit combinations do you have here? Carly? 12, right? We can just count them up here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay? If we wanted to know what those options are, we could then write them out. Pink and green, pink and orange, pink and red, pink and turquoise, blue and green, blue and orange, blah, 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 blah. Okay? And this one here, we had 8 options, without a doubt. Aiden.
So if you have one like this that has like 2 like probabilities in it, like shirts and pants, couldn't you just basically times the 2 numbers because they were?
I gotta stop calling on you, Aiden, because you just take my thunder from what's coming up. Because my next point was going to be, how much fun is it to make the probability tree? Yeah. Okay. As we can see, it gets a little bit messy if you kind of don't space it well. Okay. If you look at examples at the bottom of the page, we all of a sudden now jump to a lot more options than just 3 pairs of pants and 4 shirts, or flipping coin 3 times, right? So the second method that I'm going to show you here to get the same result, right? There's just another method to get the same answer here, is the one that you want to kind of latch onto. Knowing this probability tree and how to make it is good, okay, as a backup plan, but really plan A should be what's called the counting principle. Okay. Now the counting principle works is we focus on the number of outcomes for each event. Okay. So the number of outcomes for each event. We flip that coin our first time, flip 1. How many outcomes are there? I don't even need to make this quite this long. How many outcomes are there in that first flip? On the first flip, the very first one, how many outcomes are there? 2. Heads or tails, right? 2 outcomes. On flip number 2, and only flip number 2, how many outcomes are there? On flip number 2 and only flip number 2. Aiden?
4.
Only flip number 2. Don't worry about what happened earlier. Only flip 2, Pierce.
2.
There are, again, 2. Okay? On flip number 3, and only flip number 3. Aiden?
Is there 4?
Only flip number 3, Aiden.
8.
Don't pay any attention to what happened earlier. Only flip 3. What could happen?
2.
2 outcomes, heads or tails. Okay? And the counting principle says, if you take the number of outcomes for each individual event, don't pay attention to what happened earlier, each individual event, we can multiply these together. And what is 2 times 2 times 2? 2 plus 2 plus 2 is 6, but 2 times 2 times 2 is 8. The same number of outcomes that we got by doing that probability tree. Okay? The second one, number of outcomes. How many outcomes are there for the number of pants you can pick? How many options? 3. How many outcomes are there when you go to pick your shirt? How many shirts do you have, Sasha? 4. Aiden said, well, can't we just multiply them? And the answer is yes. The counting principle says yes, you can do that. So 3 times 4, the number of outcomes for pants times the number of outcomes for shirts, 3 times 4 is 12. The same 12 options we got from making the probability tree. So the counting principle is much more efficient than doing the probability tree. The advantage to the probability tree, though, is that it also tells you what the outcomes are. The counting principle only tells you how many. The probability tree tells you what they are. Heads, 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 tails, etc. Okay? So each one has the advantage, and which one you want to use will kind of depend on whether or not you need the outcomes. If not, then the counting principle is a great way to get there. Yeah?
So on the test, would you require us to write down all the possible outcomes?
Not for CO66. No. Okay? All right, let's look at some more challenging, well, I shouldn't say challenging, just some bigger situation things here where a probability tree would be an absolute nightmare to make. Okay? You all have made passwords for things before, right? So you know how passwords work. Some sites require capital and lowercase, some require punctuation, a special character, some require numbers. I mean, there's a whole slew of things that some sites might require. But let's look at this. A password with 5 letters that may repeat, okay, not case sensitive. How many possible passwords can be made? Let's just, don't write this down unless you want to, but let's just visualize what this would look like using a probability tree. If you've got 5 letters in a password, your first letter could be A, right? What could you pick for your second letter? Aiden. Or A again, right? Because letters can repeat. So you could pick A, or you could pick B, or C, or D, E, F, G, H, I, J, K. And then for each of those lines, if you pick A for your second letter, what could you pick for your third one? A, or B, or C, or D, or... Can you imagine that probability tree? Nightmare. Maybe make that a math packet question, right? Nightmare. So the counting principle is definitely something to know for these larger situations here, because instead of doing that probability tree, we kind of look at our chart here, number of outcomes, okay? How many letters could we pick for letter number 1? Aiden.
1 letter? Oh, 26.
26, right? We have 26 options. We're only picking one of them, right? But we have 26 options, 26 outcomes. How many letters could we pick for letter number 2? 26, because letters can repeat. How many could we pick? I'm going to kind of abbreviate this now to just L3. How many letters could we pick for letter number 3? Sasha? 26. How many could we pick for letter number 4? Anybody? 26. How many could we pick for letter number 5? 26. Okay. So the question of how many passwords exist, the counting principle says we are going to be taking 26 times 26 times 26 times 26 times 26. Woo. That ends up being 11,881,376. Just a 5-letter password that's not even case sensitive. You've got nearly 12 million possibilities. That's a lot, right? That's a lot. Any questions on what we did here? Aiden?
Yeah, but like, how many do you think you'd take away if it actually had to be like a word?
Well, passwords usually don't actually need to be words. I mean, so I don't know how many you have to take away, but usually passwords are not. The computer doesn't care what the password is, just that you have all the special requirements and stuff. Okay. Let's look at the second one here. How many possible passwords can be made if letters could not repeat? Right. So here's a special condition that's going to affect the total if letters cannot repeat. Let's make our table here. Number of outcomes. How many letters could you pick for letter number 1? Leah? Still 26. But whatever you chose for letter number 1, you can't choose for letter number 2. Because in this situation, letters cannot repeat. So how many options do you have for letter number 2? Yeah. Now 25 instead of 26. How many options do you have for letter number 3, Maggie? 24, right? It's decreasing by 1 each time because whatever you chose previously, it's going to affect what you can choose going forward. Because you have that condition of them not repeating. So how many letters can you pick for the fourth one? Aiden?
24?
No,
23?
23. 23. And then how many letters could you pick for letter number 5? 22. Right? It just goes down by 1 each time, because each time you pick one, it's then off the board. So if letters cannot repeat, our calculation changes to be 26 times 25 times 24 times 23 times 22. So 26 times 25 times 24 times 23 times 22 is a mere 7,893,600. So just by making that one little change, you've knocked off nearly 4 million possibilities. I find that to be kind of crazy, right? Because it's not much of a difference. This calculation doesn't seem like it would make that much of a difference from the top one, because we're only going down by 1 each time, but 4 million password possibilities lost just by saying letters cannot repeat. Okay. Questions on this? You've been troopers, but anything that you're wondering? All right. Let's look at the second page. Your job, and I highly recommend using the counting principle for this, but you do need to show your work in the sense that at the very least, you need to show me what you're multiplying. You don't have to make that whole big chart that we did. I mean, it's not that big, but you don't have to make the chart that we made on the first page, but you have to show me what you're multiplying using the counting principle to get your answer. So you flip a coin twice and roll a 6-sided die once. How many outcomes are there? I'm still learning how to do this, so I'm going to make my table. Okay. What are the events? We are flipping a coin twice, so we'll call that F1, flip 1. We have a second flip, because we're doing it twice. And then we're rolling a 6-sided die 1 time. So R1, we'll call it there. And how many outcomes exist for flip number 1? Connor? 2. Heads or tails? How many outcomes exist for flip number 2? 2 again. Heads or tails? How many outcomes exist for rolling that 6-sided die 1 time? 6. A 1, a 2, a 3, a 4, a 5, or a 6. So the counting principle says, hey, we can multiply all these together. 2 times 2 times 6. There are 24 outcomes that exist. Maybe you get a heads, and a 3. Or a heads, and a 5. Or a heads, a tails, and a 1. Or a tails, and a 6, right? There are 24 different possibilities, different outcomes that exist from this. This is what I must see on your page. I need to see how you get to that 24, what you are multiplying by. I recommend, if you're still kind of shaky on it, to make that chart to help you. But if you don't need it, I at least need to see what you multiplied by. All right. Any of these, as you look through them, that you'd like to do together? I'm willing to do one more of them together, except for the last one, the telephone number one. But any others? Gavin? The card one. Which one's that? Oh, okay. This one here. From a standard 52 card deck, picking a card, not replacing it, so you keep it, you don't put it back, and then picking a second card. How many outcomes could you get? So number of outcomes. What are our events? We have card number 1, and we have card number 2. C1 for card 1, C2 for card 2. From a standard 52 card deck, if we take a card out of the pile, how many options do we have? How many cards could we pick? Yeah. Our first pick. We have the whole deck in front of us. How many possible cards could we pick? 52, right? We could pick any of them. Okay. Now, reading these questions is important here, because whether or not we put the card back, that's going to affect our number of outcomes for our second choice. In this case, we do not replace it. We keep it. So how many possible outcomes are there for our second card pick, Annika? 51. Kind of like that same example with the passwords on the front page, the first one, where numbers, or they couldn't repeat. Similar situation here. We're not putting the card back, so we can't pick it again. That means there are 51 cards left. And 52 times 51 is 2,652. For you Texas Hold'em card-playing poker fans, that's how many starting hands are possible. All right, you're dealt your first 2 cards, 2,652 possible starting hands. Okay? So that's the gist of CO66. Again, don't skimp on the work. This is what I must see. If you make the table, I recommend it. But if you're comfortable with that, you're past that point, I at least need to see what you are multiplying. Questions, comments, concerns, complaints, comments, congratulations, or criticisms on this? All right, your homework is to finish CO66, and that is how you math. Don't forget to like and subscribe.